All right. Hello, everybody. Welcome to CoqPL. There are a couple announcements I want to make, so changes to the schedule. So first of all, we added a session with the Coq development team, the traditional session at the end of CoqPL. Eve will give a short talk, and then you'll have a chance to ask Coq developers about what's in the works, what the plans are, perhaps even give feedback. The other change is that there is lunch. It is not on the schedule, but it will be in the usual place upstairs. And with that, I think we're done with announcements. I'll give Benjamin a chance to introduce himself.
Good morning, welcome. We are delighted to have you here for CoqPL. We're not going to talk for a long time because we have a super exciting invited talk, which I think Tej is going to introduce.
Yeah. So with that, we'll go to the invited talk. Sam is going to tell us about a new way to smoothly handle non-determinism in programming language semantics. Sam, go ahead.
Okay, is my mic on? Is that good? All right, yeah. So at the beginning of my PhD, I started writing a little verified compiler, and I got annoyed by some kind of existential at some point. So I came up with a state with a semantic judgment that worked a little bit better for that by putting in a post condition somewhere. And then a little later, my colleague, Andres Erbsen, came along and said that he had done some kind of judgment like weakest precondition, but a little bit different. And then I was like, oh wait, I'm basically almost already doing that. Let's use the same. And then a little later, our advisor, Adam Chibala, talked to Arthur Chargereau about this style of semantics. And Arthur said, well, wait, I'm doing this as well, except we were doing it for imperative languages, and he was doing it for functional languages. And we said, well, there's something cool, and let's write this up. And so we did, and also now there's a presentation. And I would probably some of you already have used this, I would guess, but all the implications and coolness of the judgment deserves a little presentation, I believe, and I'm very happy to give that presentation. So this talk is really about how to define and use programming language semantics in the presence of both undefined behavior and non-determinism. By undefined behavior, I mean the program gets stuck, or all these ways of saying it. In terms of state transition diagram, I mean there's a non-final state without any outgoing transitions, or in the case of non-determinism, I mean that there are several possible outgoing transitions. Why are these two useful? I think I don't need much convincing here. The classic thing for undefined behavior is that you have an f of a where f is not a lambda, or in more lower level languages, very useful is out of bounds rights that you don't want to put around like safeguards around that are too expensive. And for underspecification, at the very end, the machine on which you're running your code always does one thing. So in reality, there is no non-determinism, but non-determinism is just a really useful specification device. For instance, there's things like returning a return value by malloc or reading input, or it's of particular interest, taking the address of a local variable. That's some address on the stack. And we model this as an instruction where you can stack alloc and bytes, and then within this body, you can use that address. And what this stack alloc returns is really like a non-deterministically chosen value. That's the way we believe this should be modeled, and I will show you how well this works in our style of semantics. Just to maybe disappoint you right now instead of at the end, the scope of what we're doing here is we only focus on demonic non-determinism, but not angelic. We support both internal and external non-determinism, and don't even have to distinguish between the two. We only focus on non-determinism caused by underspecified operators. And if you're interested in concurrency or underspecified interleaving, you can probably do it with our semantics, but I don't claim that we make any improvement in this very difficult domain. So non-determinism doesn't necessarily mean concurrency, even if that's probably what it implies when you hear it. I will basically, my goal is to improve on big step and small step semantics. I just put a few rules down here to get you warmed up, but I believe you all use these in your daily life or have at least seen them. Here it's for a little imperative language, but all of this also works for functional languages. The first problem I want to tackle is how to express the statement program C, when run in state S, safely terminates, and all possible final states that can be reached satisfy a given post condition. That's the statement that I basically always care about in my research. I don't know about you, but for me, this is really important, this form of statement. And when you try to write the statement down formally, if you're in a deterministic language, you just need to give a final state as prime, and then you can write it down as follows, and it's all nice. Or in small step, it would look like this. But as soon as you have non-determinism in your language, that's not what you want anymore, because the mere fact there exists one path to a state where the desired post condition holds, that's not enough. That there could be another one that gets stuck, but then this statement still holds, but it forgets about this stuck state. So again, remember, here is a state, but if you don't like state, think there's no state and it's a functional language and things still apply similarly. Now, in order to fix the situation and still support non-determinism, people have come up with various ways. So for instance, in small step, you could write a long formula like this, and it would probably mean what you want. You could also add a separate safety judgment, but that means you need to write one rule for each construct of your language, and then this is a separate thing, and you have to carry it around, and it's kind of cumbersome. Or you could also like complete the rules so that your judgment returns like an option, basically error or okay, and then for each construct that you have, you actually need several error rules that propagate everything correctly, and it's also a bit cumbersome, and I think we can do better than that. Then the second problem that you encounter when you want to try combine undefined behavior and non-determinism is that compiler writers always prefer to write forward simulations instead of a backward simulation. And in the case of deterministic languages, fortunately, forward simulations and backward simulations are equivalent. So the trick is you just prove your forward simulation, and then you apply a lemma that allows you to flip the direction of the simulation. By forward and backward, I mean source execution implies target language execution, and backward, I mean target language execution implies source language execution. And here I simplify the presentation. I use the same state representation for source and target language, but there's it's a little small down here, but in the paper and all our work, we have a relation between source and target language, and then an existential, and it still works everything. So a little, forward simulations are easy to prove because you can do induction on the source language execution, then you simplify the compilation function to obtain some kind of symbolic target language program, and you can symbolically execute that. But if you want to prove a backward simulation, basically the problem you're running into is that given a target program, what could the source program be? And you basically need to run the compilation function backwards, and that becomes quite cumbersome. So no one really wants to write a backward simulation if it's possible to avoid them. Yeah, as I said, for deterministic languages, forward and backward is equivalent. But as soon as we add non-determinism, the problem here is that in the target language, we could have the situation that we go somewhere else at the non-deterministic choice. And so it's not sufficient to just show one path through the execution. And then one potential fix might be to say, okay, let's just make the target language deterministic and keep the source language non-deterministic. But then most likely, you will simply not be able to prove the simulation because you will have some non-deterministic choices in the source that you can't represent in the target. Whereas backward simulation is still everything fine, because you have that's really the statement that you want. But I think you all know that, so I'll continue. And so the goal basically is to get a forward simulation that is easy to prove, which is still as easy to prove as the one you've seen, but which still works in the case of non-determinism. Then, so I want to do a little side note on how CompSert does this. It's in one way, it's both like a beautiful trick, but on the other hand, it's also not satisfactory. So what they do in CompSert is they just make the target language and all the intermediate languages deterministic, and then that basically solves your problem. So in the case of memory allocation on the stack, I call this alloc A. I think that's the way what it's called in C. And this should really, it can return any pointer. And in C, pointers are 32 or 64-bit integers. So from a state diagram point of view, this should really be return any possible 32-bit pointer. Whereas in CompSert, pointers are pairs of, oops, I want this one, yes. In CompSert, pairs are pointers are a pair of a block ID and an offset, and each allocation deterministically returns a block ID which is just one more than the previous block ID. And like this, the language is all deterministic, and it's all beautiful. You can still use your forward simulations. But it's, in a sense, it's not that realistic, I would claim, and especially if you're trying to combine combine your compiler correctness theorem with the proof of a formally verified processor, which we did in our PL'23 project, then if the gap between what's happening on the processor and the way you modeled your compiler is too big, you incur a lot of more work burden there. And moreover, compiler phases that introduce or remove allocation become particularly hard in that setting. I haven't done any of these myself in the CompSert setting, but from what I understand, if you have a source memory that looks that contains, say, some bindings like this, and then your target program does more allocations, then basically, say in the spilling phase, it would have done one more allocation here. These indices, these block indices, get shifted, and therefore you have to use these famous memory injections, and people tell me that these are hard to use, even though beautifully defined. But I'm so I think we can do better here. So to summarize the two problems, I want to express this statement concisely, and I want to use forward simulations for my compiler correctness proofs. And there are also further benefits that I will talk about, goals and benefits that I will talk about a little later. So I will show you a new star judgment because it's somewhat almost obvious, I will claim, and Steve Schaffer and some colleagues have already presented such a judgment at CPP 16. And as I said, probably some of you have used something like this as well. So that's about as new as it is. But definitely, I think it has been underappreciated. So that's why I'm talking to you about it. So the solution is that one derivation talks about all possible non-deterministic executions. So we define a judgment that's written as follows. It has just a postcondition instead of a final state on the right-hand side of this down arrow. And it's defined to mean exactly this statement that we want. And to give you a few sample rules, so here is the judgment for assignment of program variable y to program variable x. And so y must be bound in the current state. And what we need to check is that the postcondition holds for this updated state. And in traditional Bigstep, this rule would look as follows. So here is no non-determinism yet, but that's just like one sample rule in Bigstep style. Another sample rule is an interesting one. It's the one for sequencing a command C2 followed by a command C2. Here you have to give some, I call this mid condition, as because it's a condition appearing in the middle rather than a post condition. So you have to show that C1 in state S steps to this mid condition Q, and then that for all states in that mid condition, the program executes as you want to the final post condition. And the really important part is to put this for all here rather than just one of them, which just one of them is the case in the traditional Bigstep. And now here's the interesting one. Say I have a pseudo-random generator, which is supposed to return a number between 0 and n. Here, I introduce the non-determinism by using a universal quantification, and I can quantify over this range of values, and I assert that the post condition holds for all possible values of this n. Whereas in traditional Bigstep, especially for all, for all possible values of v, of course. And whereas in traditional Bigstep, again, I only say something about one particular value. So this is, if you think of this for all as like unfolding it on top of this hypothesis line, you can think of this as a proof tree that gets like more branches here. And if you think of it like this, I just have to repeat one more time because that's the important thing. So one proof tree over which we can do proofs by induction contains all possible executions. And especially for induction, this is really cool. So now if you have no bound here on the random number, and you would say this is specified as returning an arbitrary size integer, then you can actually get infinitely branching proof trees. So you could have more and more proof trees all the way here. And then you could even think of each of these proof trees might do exactly v loop iterations. So you could actually get a proof tree that becomes higher and higher and higher as you move here. And you could get a proof tree of unbounded depth, even though each branch in this proof tree is finite. So I think for practical purposes, we don't really have infinite data, but it's kind of fascinating to see that you can get this kind of infinity and still do induction over it. I think other people tell about, oh, they need ordinals, and we actually get ordinals, something similarly powerful as ordinals just by using Coq's inductives. So yeah, that's cool. And now some relationship to traditional semantics. So there is an equivalence between our Omnisemantics Bigstep judgment to traditional operational semantics in the following sense. If you also need to add this safety judgment, and here I define this to mean the term is not stuck and also terminates. I will talk more about termination and non-determination, how we're not very good there later. And so that's the equivalent. That's the equivalence. And this is particularly useful because if you want to sell your proofs and you're using Omnisemantics yourself, but maybe the community is not yet so convinced that this is the way you should do it, then you can use Omnisemantics internally and enjoy all the benefits. But then when you want to sell it, you just use it to get a statement which looks like all traditional. You discharge this one with a program logic, and at the end you can get an end-to-end theorem that looks like all familiar, and people will not question it too much, even though you used your cool one inside. It's also equivalent to a weakest precondition semantics. It's actually like the meaning is just the same. That's really cool. And but the way it is defined is a little different. So there's three important differences. And here I'm thinking of a weakest precondition generator defined using inductive rules rather than fixed point. But if you use inductive rules for that one, then the weakest precondition not generator, but weakest precondition judgment will have proof trees that contain only one rule application per loop construct, whereas in our Omni-Bigstep semantics, we do one rule application per loop iteration. That means we do some kind of unrolling. That means that a weakest precondition needs invariance for loops, whereas we do not. We need invariance because we just like unroll and until it's done. And also that means that the structure of weakest precondition proofs mirrors the structure of the commands, whereas the structure of our Omni-Bigstep derivations mirrors the structure of the execution. And mirroring the structure of the execution is important if you want to do induction over an execution. Another thing to be said is that this post-condition is really a post-condition in the sense that it's an over-approximation of the set of results. And for instance, in this one, we could just set it to true and the statement would still hold. And that is actually desired because it means that at each reasoning step, we can lose some precision if we think this is useful for our proofs. We're not forced to always deal with the precise set. That means that the rule of consequence holds. And for a while, we thought that actually you can't even define a precise judgment. Then we thought a little harder, and you can define a precise judgment. And we wrote it down, but it's just more cumbersome, and we don't really see any use of doing it. So you can see here we have our rules, and here we have some precise rules. And especially for the let, you need to like do this union overall over a family of mid conditions. It's like you can do it, but there's just basically no point. And you can always, you can also, if you have our Omni-Bigstep definition, you can always say you can get the strongest postcondition if you take the intersection of all provable postconditions. So if you really care, you can get it. So to summarize, to come back to the two problems. So how to express this statement that I care about? It's just by definition, we can just say this and we're good. And now for the forward simulations, it just works as I will show on the next slide. So here again is a traditional forward simulation in a non-deterministic setting, which does not what we do, which does not do what we want, because I mean, in the statement there is no existential, but morally there is somewhat an existential in the sense that you show that you only show one execution rather than all of them, whereas Omnisemantics forward simulation really has this built-in for all, in the sense that whenever you do a non-deterministic choice in your target language execution, you have to show the precondition for all possible values of the non-determinism, and therefore, like you prove the things for all your possible executions, and the statement is just still what you want. And you can also prove this, as I will show a little later. Actually, I will show it right here. So I want to show you that Omnisemantics forward simulation is the same as a backward simulation. And I will just do a little magic by unfolding some stuff. And I think I think for this audience, I want to show this little proof. This is the statement I had on the previous slide. This is the compilation function. We have source language execution implies a target language execution. Down here, this is how I write down backward simulation for safe programs. So that's a big, an important assumption. And safe means no undefined behavior, and also that it terminates. So if the way I express backward simulation is if the source program executes safely, then the target program executes safely as well. And for all target executions, there exists a corresponding source execution. And I will show you that this one implies this one by first putting in a little more space, but otherwise it's still the same. Then next, I use the equivalence that I showed you on the previous slide to express these omnisemantic stuff in terms of traditional semantics. But other than that, that's just that step. And then I set the postcondition to the strongest postcondition expressed using traditional semantics. And if I do this, I just replace that P by what I wrote like here. And then notice that this implication here is just the identity. So I can scratch it out, and boom, magic, I get a backward simulation. And so this is the magic for again with the same state representation, but you can do the same trick also with existentials and the relation between the source and the target language state. Now, with Omnisemantics forward simulations, compiler phases can easily introduce nondeterminism, eliminate, that is, resolve nondeterminism, or preserve the amount of nondeterminism. And I will give you an example for each of these three. The example is taken from our Bedrock 2 compiler, and it uses stack allocation as an example, but it's the same on higher level languages as well. So, how to introduce stack allocation, that is, introduce nondeterminism. Let's consider a source program that is some function body, which is compiled by the compiler into a program that does some stack allocation in order to have a space, say, for some variables that it needs to spill, and then the result of compiling the function body. So in the source, for this snippet, there is no nondeterminism, but in the target, there is nondeterminism called by this nondeterministic call to allocation, because the stack address could be any value. And so the rule for proving, and yeah, we're going forward, so given this, we have to prove this program. And the rule for proving a stack allocation might look a little bit like this. It has this universal quantification over all possible addresses that could have been returned. The rest of the program has to be correct. And so if you apply this rule, you have to show its premise. And in order to show this premise, you can just introduce this address, and then you get a universally quantified address, and you have to prove your correctness of the compiler for all possible values of A. So that's it just naturally happen. Naturally, the Coq shows you the goal that you would expect to have to prove. Similarly, if after that pass, you have another pass which eliminates your stack allocation. For instance, it will probably do something like decreasing the stack pointer and then say, okay, now at the stack pointer you have that amount of space. So here we have, that means we're in a situation where the source program does have nondeterminism, but the target program has no nondeterminism because only one concrete value, namely the stack pointer, is possible. And again, here it means you get to invert basically the induction over the source execution. So you get to invert this rule, so you can use this one. So you get a hypothesis which is universally quantified over the address, and you have a concrete value of the stack pointer. So all you need to do is you instantiate your hypothesis with one concrete value, namely the stack pointer of this address. And finally, a compiler pass that preserves the amount of nondeterminism would simply say, okay, here I take, I get the rule again here, and I get it here, and I just introduce that value for the address that I got in the target execution, and I instantiate the source execution with that value. So to summarize, passes that introduce nondeterminism just has to prove that for all target language nondeterminism, the compilation is correct. If they eliminate it, they can instantiate a quantifier that comes from the source execution. And if they preserve, you take the one from the for all from the target to use it to instantiate the for all in the hypothesis. So yeah, all simple. One thing though remains is, what about proving code with semicolons, like these semicolons here? The rule that I showed you is this one. So you would think you always need to come up with this mid condition. Isn't this super cumbersome to come up with it? And indeed, it is super cumbersome if you're trying to use this rule. However, you can prove a CPS-like chaining lemma by instantiating this queue with the weakest precondition. You get this chain-like rule, and this one just gives you, like, if you go forward through, step forward through your program by applying this rule, this problem is beautifully solved. On the other hand, sometimes you get an inductive hypothesis that prescribes a mid condition for you, and in that case, you can use this one. Or if you're in the other case, you can also use the weakening lemma to get like an EVAR in CoqSpeak. All right, so far I've talked to you about Bigstep, but it turns out the same pattern also works for small step. So in traditional small step, we have like a one-step thing, and then we use the reflexive, transitive reflexive closure to lift it to multiple steps. We can do almost the same in Omni small step. So we have a command which say it takes one step, and after that step it satisfies postcondition P, and then we lift this to multiple steps using an operator that we call the eventually operator. We denote it with a superscript diamond, and it has some very similar flavor to the chaining rule in the sense of the sequencing rule in the sense that you first do one step to this kind of mid condition, and then for all values inside that mid conditions, you have to show that the rest executes as expected. Also, yeah, here's a kind of the whole zoo of you can do imperative, you can do functional with state, you can do functional without state. At the top, I always write the traditional one, and then at the bottom, the corresponding Omnisemantics one. And I think we've tried out all of these, and they all work fine. So yeah, in whatever of these cells your work is, you can use it. Here's a little overview, just a few small step rules. I will not comment on all of them except on one, which is kind of interesting because it shows you that you can like step a subterm. If a subterm takes one step, then you have to show that the outer thing also takes that step, and then you can prove that's the rule you need for this. Then here we also noted that you can use evaluation contexts. It took us a while to figure out that this is actually possible, but it is, so good news. It's actually for Bigstep, and it gets rid of some constraint that we had before, that you could always only do a Bigstep for functional language using a normal form, but I think this one helps with that. There's more about this in the paper. And another thing you can do is if you take the exact same set of rules, but say we consider it as a co-inductive rather than an inductive, you get a statement that also means something. It means that every possible execution either terminates in a state that satisfies the postcondition, or it diverges. And the or it diverges, that's not a very strong statement, and we're a bit unhappy about that. But if you think, basically you can do termination insensitive reasoning using these co-inductive statements. And same also works for for small step. And however, a bit of an open question is how can we use Omnisemantics simulations to prove preservation of both termination and preservation of divergence? We have some plans there, but it's just not fully worked out yet, and that's I think it's somewhat a big drawback from a theoretical point of view. But I will show you that from a practical point of view, what I want to hack, it's not a problem, because in Bedrock 2, we do enforce termination of all programs because I think termination is an important correctness property. But then the only place where we need infinite execution is really because our systems are so simple that we just do have basically a embedded program with a top-level structure that looks like this. We first init and then just while through handle one event. That's basically as fancy as it gets in our world. And for this one, I just wrote like manually a few RISC-V instructions that jump back and back here and proved it like at the RISC-V level without using the Omnisemantics judgment, but only the small step one. And then we have this invariant that holds after each RISC-V level instruction, which says that after a finite number of instructions, the RISC-V machine will reach a state which corresponds to a source language state at the end of a loop iteration. So there's a little manual work around it, but then we can use this for an infinitely reactive system. And now two more applications. One is that you can use this in type safety proofs. And so traditionally, to prove type safety, you prove progress and preservation, and that's all nice, except that if your language becomes a little bit large, you get a quadratic proof term. Because what you do is you have a typing derivation and you have a evaluation, one-step derivation, and you can either do induction over this one, and then you have to invert this one to show to discard most of the cases, or you can do induction on this one and invert this one, and again discard most of the cases. So you treat you do as the proof writer, you only treat a linear number of cases, but under the hood, Coq needs to treat a quadratic number of cases by discarding most of the other cases. So overall, it results in a quadratic proof term. That's one disadvantage. And the other one is that you also basically do two proofs. You first do progress and then preservation. So you go through all your language constructs twice. And especially the part of going through all your constructs twice, that already when I was a master student and worked on the theory behind Scala, we were already bothered by that. And the thing we proved was not actually this, but we proved this. So we call it a combined type safety statement. And for all our Scala dot, it was called proofs, we proved this one. And fortunately, that calculus was deterministic. So we were basically allowed to use this existential here without missing any cases. And I think we derived then a progress and preservation from it to make people happy who prefer this one. And this one worked beautifully for our deterministic language there. But as soon as you add non-determinism, this existential is not strong enough. You would want a for all there. And if you use Omnisemantics, you just prove this statement. Here I wrote this set as a set, but you can really think of it as a postcondition. You say for each term t that types, either it is already a value or it can take a step to some t that, again, has the same value, so it's preserved. Type is preserved. And this one has, so advantages are you only need to go through all the statements once, and the proof term size is linear in the number of constructs. Now, okay, I mean, it's about good. So I want to talk to you about how to derive program logic rules. You can do WP or HOR rules. In the case of, so WP is really close. So Omni-Bigstep and weak precondition already have the same signature up to argument reordering. And so if you define, so this might be a bit confusing, but here I meant if you already have a traditional definition of WP, then it is equivalent to our Omni-Bigstep. But in our case, we don't even bother defining a traditional one, but we just define the WP as being our Omni-Bigstep judgment. And then for the proofs rules, you can reuse most of the constructors of the inductive prop, except that you want to do two changes typically. For the loops, you want an invariant-based one rather than one that unrolls each step. But that's easy to prove. And then also you prefer a chain CPS style judgment for the sequencing rather than the one that requires this mid condition. But it's really easier to derive. And then, yeah, time for some controversial opinions. In my opinion, and some other, I'm not sure about Iris folks, but I've seen Iris folks do a lot of WP instead of HOR. And so, yeah, controversial opinion, you don't even need HOR, but if you, sorry? Okay, some Iris, okay, good. Okay, anyways, so, but if you still want, and apparently some people, including one co-author of mine, really find HOR is cool as well, and it's really easy to derive HOR rules. So you can just define it as follows, and then derive them. And one cool thing is that without our semantics, you get this problem with the baked-in frame rule. So basically, if you have a deterministic language, you can define a bad HOR triple as follows. It doesn't mean what you want. It makes no sense to me. but you can then use this so-called baked-in frame rule technique to fix the situation by universally quantifying over all possible frames, and then you can get back the meaning you want, as long as your language is deterministic up to the choice of memory addresses. So yeah, I mean, people have used it and apparently are excited about it, but it also requires this two-stage construction, and all of this is not needed anymore if you do Omni-Bigstep semantics. You just define your Hor triples as follows, and then your frame rule holds. And the key helper lemma that you need is really that if you augment your state or your memory with some disjoint as2, then the derivation still holds and doesn't modify as2. That's the way the frame rule looks without Hor. And yeah, we proved this one for both Arthur's language, and also recently I proved it for our language, even though we don't really need it because we already quantify over the frames elsewhere. But yeah, it's good to know that it holds, I would say. A few limitations. So it doesn't really help. I think it neither helps nor hurts with underspecified evaluation order and interleaving of stuff. That's just not the domain where we're trying to improve things. If you want to rearrange, do the non-deterministic choices earlier or later, I think if it's just very visible how far you move and it's very local moves of your non-determinism, it works, but not longer moves. They probably want to sell me prophecy variables. I haven't tried it out, but on my list. Yeah, okay, yeah. I don't know how they combine, how they would combine. And then one thing I'm a bit bothered is, yeah, support preservation of non-termination. We're not there yet. It might work, but it's like a little, yeah, not so good yet. And then sometimes when you do induction, you get like one derivation that shows a first postcondition, and then maybe a helper lemma shows you a second fact about things, and then you need to combine them using this intersection lemma. And then sometimes you don't quite like this, and then you just say, okay, I put both into my induction hypothesis and prove them at the same time instead of using the intersection lemma. But in the work I did, it only appeared like once or twice, and in some other work it appeared more often, and I'm not yet very clear about that, but not that bad of a problem, I think. And so to summarize, one Omnisemantics derivation talks about all possible executions. Therefore, it solves several problems that arise from the combination of undefined behavior and non-determinism. We can express this judgment that I care about, and you maybe too, just as by definition as follows. We can do forward compiler correctness proofs, which just work even if we have non-determinism and undefined behavior. We can do progress and preservation in one combined linear size proof, and termination-sensitive program logic rules are really easy to derive. So with that, I'm at the end of my presentation. I have a very short blog post of the gist of this presentation up here, and then we wrote a paper about it, which will appear at CoqPL' shortly, but for now you can find it on the HAL archive. And with that, I'm happy to take questions.
All right, we have a bunch of time for questions before the next talk.
Hi. Yeah, thanks for that. That's a really nice working out all these details. Very nice to see it like all in one package. I was wondering one thing you mentioned in the beginning, that you don't do angelic non-determinism.
Mm-hmm.
Is it? I mean, naively, I would just think you replace the for all by an exists, and then you have angelic non-determinism. Does that work? Does something go wrong?
Ah,
have
good
you not
idea.
Tried?
Good idea. I mean, written down as a coqproc, it would probably not even have an exist, but it would just be baked into the constructors of my inductives.
The implicit exists of
yeah,
the
the implicit exists. I haven't done it, but as you say it like that, probably. I don't know. Yeah.
Okay.
Yeah. Probably. Yeah.
Also, thanks for the talk. I have two small remarks.
Mhm.
One is you said that if you do traditional progress and preservation, the proof term will become quadratic.
Mhm.
Have you heard of this trick called small inversions by Monin? That allows you to do
Ah,
inversion in a way that the size is that the proof
have
term does not
Okay.
become big.
Okay, nice.
It's
Good
a
to
very
know.
elegant trick, and I recommend you and anybody else here to read
Okay,
about
so
it.
small inversion is the keyword.
Yes, so
Okay.
that's the title of the paper.
Okay,
uh,
nice. Is it okay? Okay, so okay, good, good, excellent. Okay.
The second thing, at slide 27,
Mhm.
you said that in C, the memory model, the pointers are just integers. I
Oh,
think this is a
probably not
very,
wrong.
very, very common misconception because in the C community there has been like a large topic of debate of how to represent pointers, and especially the group of Peter Sewell, but I in my PhD thesis have been wondering about that.
Mhm.
And currently, one of the proposals at the C Standards Committee is that there should be an integer together with something called a provenance.
Ah, yeah. Yeah.
So it's a bit more complicated.
Yeah, good point.
So
Yes.
I would call it C-like or something like that.
Yes, definitely. Okay, yeah, because indeed, I'm working on Bedrock 2, which we call a C-like language, and we say we don't want all of the pointer provenance business, but indeed, yeah. So yeah,
Okay.
good point. Yeah.
So you mentioned some difficulties with proving preservation of non-termination of non-terminating executions, but you also mentioned that you have a small step variant of your approach, which is just describe transitions, non-deterministic transitions, but transitions. So based on these transitions, can you do concert-style simulation diagrams that would prove both preservation of both terminating and non-terminating behaviors?
Yeah, I mean the problem, it's not quite sufficient. What I'm doing, it's not quite to our small step thing is not quite sufficient because it doesn't allow non-terminating executions. Our our eventually operator still requires you to be terminating. Where is it?
Yeah, but could you have a forever operator that
Yes,
makes it possible to have
yes,
infinitely many
yes,
conditions?
indeed.
Yes, that's the
Yes.
question.
So my co-author Andres indeed wrote down a forever combinator and combined some inductive and some co-inductive and wrote like a very small example, and it's just a bit cumbersome, and we haven't yet pulled it into the real thing, the compiler. And it's a weird stuck. I mean, we're a little stuck on it, on making it work, but fundamentally, I think, basically, might work. Yeah.
If you rewrote CompCert in an Omni style, what would happen?
Good things, I would assume.
You can support more pointer with less effort in the semantics proofs. The original CoqPL' semantics has this symbolic model of memory and pointers, and you have to work very hard to relate arithmetic to that model. And many papers showing how to extend the model. You allow different kinds of arithmetic. You don't need any of that if your pointers are not readable.
Well, that's the wrong model.
Yeah, yeah.
Sounds like a good thing.
I think there's some legitimate language and semantic design questions here. If you want to see like language that has as simple as semantics as possible, then things don't work out. And pilot proof using this technique, you might have other reasons for.
Well, you can define such a language, it just wouldn't be C.
Also, I think we've got some problems with some possessions. Like whenever you have a local variable, and then you have a function call, and then after that you want to inline a local variable. I don't think you can do this in these kinds of complete memory models. But in CompCert's memory model, you definitely can. Something that program does, in essence.
I think it would actually be an interesting question to figure out how much optimization we can do with such a language. It's something that comes up a lot in discussions with Rust.
Yeah, the question In your example about co-inductive semantics, you mentioned divergence as a possible outcome, but should you only have divergence and termination? Shouldn't there be more than that?
Yeah, I mean, I would really like to have like infinite, like reactive divergence, silent divergence, termination, and stuckness, like the way it's done in CompSert.
This is what people who are programming are actually looking for.
Yeah. I would like to do it, but that's exactly the part that we haven't figured out yet fully. So right now we're doing only terminating, and then this co-inductive thing, which doesn't quite do what I want, and therefore we're not using it. But yeah, I think we should really just work out the co-inductive thing as Xavier suggested, basically. Yeah.
Just a very small, in the same vein, you could probably also do a version with step indexed judgments.
Ooh, probably.
Could you?
I haven't. Okay, I've worked with VST, and under the hood there was step indexing, but I haven't worked on it myself. So it better don't make statements here.
I have a quick question. Do you think that this is a good semantics to learn as your first semantics?
Ooh, no.
No. Okay, that's a very clear answer.
Yeah. No, I mean, just even if it's like small step and big step have been around so long, if you want to understand the literature, that's what you need to learn first, anyways. So,
okay, I was wondering if you should start with this and then only relate it later to small step.
I don't know. Probably not.
Okay.
Ralph has a question.
Yeah, this is somewhat related. So if I use this style to define the authoritative semantics for my language, where I say this is the definition, it's not like there's some equivalent version of a small step. Well, A, do you think that would be a good idea? And B, isn't there some risk here because I might define the rules for a particular construct in a way that the precondition I'm defining is unsatisfiable, which basically means I'm introducing allowed stuck terms because your calculus will say that's fine. I mean, essentially this would be, I think this would exactly correspond to what's sometimes called no behavior. So is that is there a risk of introducing that accidentally, or is it a feature that I cannot have this in my language, or what would you say about that?
I think it's good to go for authoritative semantics. But yes, indeed, there is the risk. But it's. I mean, you can also get accidental stuckness if you forget. Like in traditional small step, you can forget one rule, or you can forget about the base case and write compiler correctness proofs which don't mean anything because there are no base cases. Something like that can happen as well. So. And then regarding the no behavior, where you basically, if you quantify over an empty set in a non-deterministic case, that leads to no behavior and you don't have to prove anything. That's actually a cool feature. There's cases where you could imagine that you want to say if you exit early, you just don't want to say about anything about that, and you could do this, or you could use it to model running out of memory. So, and we actually, with our stack command, we actually pretty much did that in the sense of the judgment we defined doesn't care about whether we run out of memory, because in the out of memory case, we quantify over basically the empty set of remaining addresses. So we don't prove anything there. But then in the compiler correctness proof, I take an additional judgment, which is the result of some very dumb static analysis that tells me that I will have enough stack space and I can sign it like that. So it gives you the freedom to not care about one property at a time. And Adam,
yeah, you could also imagine using that for if you encounter a hash collision, right, in an execution.
Yeah, I just wanted to give another answer there, and I'm remembering it's probably good to talk into a microphone when I answer. I think this is a good choice for the authoritative semantics of a language in the middle of a stack where you're going to prove everything, so it won't be in the TCB, but it is kind of the right way to think about one particular level.
Yeah, I agree.
we have a couple more minutes before the next talk.
In terms of Coq engineering, if you want to do Omnisemantics smoothly in Coq, do you rely on any specialized tactics that you use a lot, or do you rely on any particular classical kinds of axioms, or can you all basically do this in a kind of way without axioms so that a Coq beginner can basically get through it without having to write any alt or so?
Good question. I think you can really do without any axioms and without any specialized tactics. It's just, I think that's one of the strengths of the whole thing. It like really just naturally presents you the goals that you're expecting. And also, there's no such thing as an Omnisemantics library or anything. It's just, you start with an empty Coq file without any dependencies, and you can do Omnisemantics.
Yeah, you just need Cox inductives and things about that, and that's it, basically. Is that what you're saying?
Sorry?
You just need Cox inductives, and that's it.
Yeah, exactly.
Is that what you're saying?
Yeah.
Okay, sounds like a fun student project to really do this for some other language.
Yeah, and let me know let me know the pain points if there are any. Yeah, I'd be curious. Yeah.
All right, let's thank Sam.